Hi, I'm Jacob Goss.
I'm Gary Mullins.
Sarah Ginebra.
I'm Jennifer Glendinning. And for our project, we did the DC motor car. We're group 12. So for the project, we built a variable speed vehicle capable of measuring its power draw, and we took additional measurements to determine velocity. So the car unloaded was 1.6 pounds, and with the weight, it was 3.4 pounds.
So to show you guys the car in action, we've got here the model we did our testing on. Oh, let me get the screen sharing switched. So here's the model. And as you can see, we're able to vary output speed and power as a function of this trim potentiometer. It's powered by a lithium ion battery cell here. We're using an Arduino Uno L298 in H-bridge driver, as well as the provided INA260 current sensor. And joined together with the vehicle chassis, we were able to propel this vehicle on its own. That will conclude the demo. So once we had this car made, we were able to collect data with it using the onboard sensor, as well as our external measures that we took. So we took 3 types of trials. One is just a simple spin. So the vehicle was elevated off the ground. And from there, the tires were allowed to freely spin, and we were able to measure the current it took, or the current and power it took to do that. From there, we were also able to run 2 other tests, that being a roll test with the vehicle itself and then a loaded roll test. And we were able to get power plots for all 3 of these, and we were able to get velocity plots for the last 2. This plot here shows power versus time for a simple tire spin. Moving forward, we'll look at the...
So we have a velocity plot right here, and we did that by setting out a adjacent ruler next to the car itself, and we would measure how long it took for the car to go 6 inches as it was accelerating until we got our final displacement plot, and we did this velocity graph for the car without a load and with load.
And so here was the loaded test. So we basically affixed a 1.8 pound aluminum bar to as close as we could get to the center of the car so that we could maintain traction. And we were able to collect a plot. And you'll see some main differences between power versus time, as well as displacement versus time between the unloaded and loaded versions. You can see for the loaded version, it takes more power, and you ultimately achieve a lower top speed due to the additional weight.
For the Simulink model, we focused on the actual DC motor, doing an electrical and a mechanical function and then combining them. Over there, we have the scope output of velocity and current. We can see that velocity, when it starts from 0, like spike up real quick and then go down as the velocity starts to like find like a center point. And then pretty much we use this model as well as the data collected from the real simulation to estimate like some specified parameters. As far as how the work was distributed, Jennifer built the physical model. Gary did the coding software as well as the electrical setup. Jacob also was a part of like the coding software team. And then I built the Simulink model.
So our questions that we wanted to answer from the start to the end of this lab is, what is the max velocity achievable in the car as a function of load? What is the power required to sustain max velocity? And what is power required to accelerate to max velocity? And we have a table here showing that when there's no load, max velocity is 0.844 meters per second. The power required to accelerate to max velocity is 6 watts, and the power required to sustain max velocity is 2.5 watts. And for the loaded trial, the max velocity is 0.653 meters per second. Power required to accelerate to maximum velocity is 6.5 watts, and the power required to sustain max velocity is 2.7 watts.